Morning, everyone. Happy Thursday. Thank you for joining us on our presentation for our preliminary design for this ammonia LPG tanker. We are Crossbones Cargo. I'm Aiden Chuslick, and I'm here with my colleagues,
Midshipman Eric DeWald.
Midshipman Liam Prigmore.
Midshipman Derek Bernaz.
All right. In this presentation, we will be going over the 4 systems we were tasked with designing. These are the cooling water system, the inert gas system, fire suppression system, and the cargo handling system. Let's get started with Eric and the cooling water.
So first we have the cooling water system. This system is designed to cool the main engine, the auxiliary machinery, and the auxiliary generators. This cooling water system removes all excess heat so that it can all operate within its design parameters. 3 systems were used for this: the seawater system, the low temperature system, and the high temperature system. Several major components went into the making of these systems. First is the centrifugal supply pumps. This is what pushes the water through the systems. Next are several plate-type heat exchangers, which remove heat from the system, and then the 3-way mixing valves, which allow for the control of the temperature in each system. First up, we have the seawater system. This system is operated by 3 57 horsepower pumps. These pumps can draw suction from either the low sea chest or the high sea chest, and then discharge into the central coolers and then overboard. A 2.3 horsepower pump acts as the evaporator ejector pump, which supplies feed water to the evaporator. The central coolers in this system are 2 Armstrong plate-type heat exchangers with a capacity of 12,418 kilowatts each, and this is where heat will ultimately be rejected within all 3 systems. Finally, there is an emergency bilge suction on the supply pump of number 1, which allows for further redundancy in the case of a bilge pump failure. On the other side of the seawater system, there's the waste heat condenser and the ammonia cargo condenser. Seawater was chosen for these 2 condensers as LT water would have been too warm. The ammonia cargo condenser is supplied by 2 1/2 horsepower pumps, and the waste heat condenser is supplied by 2 37 horsepower pumps, both sets of pumps drawing either from the high or low sea suction. Next up is the low temperature cooling water system. This system is operated by 2 102 horsepower pumps. These 2 pumps will discharge into the central coolers and then out into the rest of the LT system. The LT system cools the stern tube lube oil cooler, the shaft bearings, the main engine lube oil cooler, and the jacket water cooler. This main engine lube oil cooler is a Hisoka plate type heat exchanger with a capacity of 1,323 kilowatts. On the other side of the LT system, there are the main engine air coolers, main engine turbocharger coolers, auxiliary generators, AC compressors, refrigeration compressors, and the air compressors. All this machinery then discharges back into the suction of the supply pumps. Finally, there's the high temperature cooling water system. This system is operated by 2 12.5 horsepower pumps. In parallel with these pumps is an Alborg EHU25 electric preheater with a capacity of 168 kilowatts. This preheater serves to keep the system warm when the engine is offline to prevent corrosion buildup within the cylinder liners. A 5.7 cubic foot deaerating tank also exists within this system to provide for the release of non-condensable gases within the system. A float switch is installed on this purge line to alert the engineers in case of any large release of non-condensable gases, as such would occur in the event of a cylinder liner burst. And then the jacket water cooler in this system is a Hisoka plate-type heat exchanger with a capacity of 2,343 kilowatts. Additionally, the evaporator in the system can serve as an additional cooler when it is online. So this system is designed to operate at a max seawater temperature of 90 degrees Fahrenheit. This seawater will then go into the central coolers where it will cool the LT freshwater down to 97 degrees Fahrenheit. And then this LT freshwater will travel through the HT cooler where it will cool the HT water down to 160 degrees Fahrenheit. Between these 3 systems, a wide variety of machinery is being cooled, each with their different temperature requirements. To accomplish this, 3-way mixing valves were placed on the bypasses of each cooler. These 3-way mixing valves mix the warm inlet water with the cool outlet water to achieve that desired temperature. And these valves are AMOT Model G version G electrically actuated 3-way mixing valves with a maximum capacity of 3,170 gallons per minute.
The next system that our group designed is the cargo handling system for the ammonia and LPG tanker.
Primarily, the system has to be able to do its job, which is safely and efficiently loading and discharging cargo while in port, also safely storing the cargo on the vessel's voyage from Long Beach to Hawaii, and then ensuring compliance with all the Coast Guard CFRs and maximizing crew safety. As for the purpose of the different components of the cargo system, we want to maintain the cargo as a liquid because it's easier to store as a liquid, it's safer to store as a liquid, and it's easier to pump as a liquid when compared to a gas. The vessel needs to be able to load or discharge all its cargo within the 1 day it's going to spend in port in each voyage, and there will be safety and monitoring systems for temperature and pressure inside the system that is outfitted on the tanks. As for the major system components of the cargo handling system, inside the engine room we have a hydraulic power pack. This is for your remote actuated hydraulic valves. And to handle the ammonia boil-off gas, there's going to be an ammonia reliquefaction compressor and a condenser. And then the cargo piping system includes all your tank outfittings, your insulation, your pumps, motors, your radar TLIs, excess flow valves, and the suction manifold strainer. This is a broad overview without the tank outfittings of what the cargo piping system will look like. As you can see, there's going to be 4 port tanks and 4 starboard tanks. Tanks 1 through 3 port and starboard will each have a capacity of 400,000 cubic feet. Tank 4 port and starboard has a capacity of 300,000 cubic feet. This adds up to the total vessel capacity of 3 million cubic feet. This is a closer look at what each individual tank will be outfitted with. So you can see the deep well cargo pump, which is driven by an electric motor on deck, the radar TLI. There's also a connection to the suction line, the fill line, and the inert gas line for cargo operations. There's a safety relief valve in case the tank becomes pressurized, because these are going to be IMO, not type A, non-pressurized tanks. And on the right side of the tank, you can see it's outfitted with some intentionally placed temperature transmitters, pressure transmitters, temperature and pressure alarms per the CFRs, as well as a 95% fill alarm and a 98% fill alarm per the CFRs that will automatically secure cargo operations if the tank becomes too full. This is a look at what the insulation for the tank will be. So LPG is stored at negative 44 degrees Fahrenheit, ammonia at negative 28 degrees Fahrenheit. For the contract, we have these IMO type A tanks, which are non-spherical and non-pressurized, which means that they're not going to be refrigerated tanks, but they do need to be insulated to maintain the cargo as a liquid. In order to accomplish that, we're going to use polyurethane insulation, which has a very low coefficient of thermal conductivity, about 0.013. The Coast Guard requirement is 0.075, so we're at about 1/5 of that, which is a good range of safety there. And then the tank also has 2 barriers. In case of a failure of the primary barrier, the secondary barrier is rated to hold for 15 days. The main cargo pump, which there will be 8 pumps once inside each tank, is a Wärtsilä Svanehøj DW250. It has a capacity of 27,000 cubic feet per hour, which means it's capable of discharging the entire system within about 15 hours, which meets the 1 day requirement in port. The maximum fluid velocity will be 6 feet per second, and the horsepower required will be 115 horsepower supplied by that electric motor. There'll also be a slop tank, which has 1% of the total cargo capacity, which is 30,000 cubic feet, and that will have a smaller version of the same pump, which is the DW100. The hydraulic power unit located in the engine room is used for the cargo system as well as the bilge and ballast system. This is a Damco Nordic SVC 96, which is capable of outfitting 96 hydraulic actuators. Inside this system, we're expecting to have about 50, so there's room for refits in the future, or also redundancy for safety. There's 2 8 horsepower motors. This will have one of them in standby at all times for safety. As for the reliquefaction system, since the vessel is outfitted for the main engine to burn boil-off LPG, but not ammonia, we need to do something with the boil-off gas from the ammonia. To accomplish that, we're going to have a Burkhardt 2K90 compressor capable of reliquefying 21,000 cubic feet per hour. The tanks are only designed to produce about 160 cubic feet per hour, so for that reason, this system can be operated automatically or manually only when needed. And this is a look at what the cargo manifold connections. So outboard, you're going to have your main connections. There's going to be suction manifold strainer, a purge valve off the side of that, your remote actuated hydraulic butterfly valve inboard of that. Inboard of that, you have the check valve, which is your excess flow valve. So in the event of a rapid expansion of gas inside the line, It will secure flow, that's per the CFRs. And there are also some remote and local temperature and pressure monitoring devices.
All right, inert gas. Main goals of this system is to ensure the safety of the vessel, the crew on board the vessel, and meet all regulations. How we do this is by supplying inert gas during cargo discharging operations to blanket and displace all hydrocarbon vapors that are left over. Here is a look at the Alfa Laval SMIT IG generator unit. Now, let's look into the parts that make this system up. Within the engine room, we have our generator, scrubber, chiller, and dryer, the three support systems, which are supply air system, fuel service system, and seawater service system. And then before the inert gas leaves the engine room, it passes through the deck pressure regulating valve. When on deck on the distribution line, there's a deck seal, pressure vacuum breaker, 4 high velocity pressure vacuum valves, ballast tank connections, and purge pipes for the cargo tanks. We have 2 system drawings for this system. Let's start with the inert gas generator drawing. As you can see on the top left is the air supply system, on the middle left is the fuel service system, the bottom left is the seawater supply system. Centered on the page is the generator itself, and then working its way down the right side of the page is the inert gas outlet. Here's a really cool picture from Alfa Laval showing a sectional view of the generator. We could really see all the inner workings of what's going on. You can see the seawater being supplied for the scrubber on the left side and the cooling jackets. You can see the air being supplied and the fuel system. This is the inert gas distribution drawing. You can see on the top left is where the inert gas leaves the engine room and comes onto deck. It passes through the deck seal and then it's on the main distribution line. On the main distribution line, there's 1 PV breaker. There are 3 PV valves on the main line and then 1 more PV valve on the branch off line to the slop tank. And then you have your port and starboard vapor recovery valves on the cargo manifolds. Then you have your branch off lines to all the tanks. Zooming into one of the tanks, you can see on the left hand side is where the inert gas is supplied. The inert gas will enter the tank at the top of the tank and form a blanket over the hydrocarbon vapors and work its way down as the tank is emptied of cargo. And then on the right hand side is the purge pipe. The purge pipe extends all the way down to the bottom of the tank. So when discharging cargo and all the cargo is empty, there's still vapors left over, which can leave the tank through the bottom of the purge pipe. The purge pipe also extends 8 feet above deck, as per Coast Guard regulations. And then on the ballast tanks, there's connections. These connections can be hooked up with portable hoses to the inert gas main distribution line, so the supply air fans for the inert gas generator can be used to speed up the process of gas freeing the ballast tanks. Okay, looking at the system operation of the inert gas generator. The generator produces a very low oxygen content at 0.5 to 1% oxygen, also a very dry inert gas. There's also a very low percentage of carbon monoxide at a maximum of 100 ppm. This is thanks to the inert gas generator controller. This controller continually monitors the oxygen content and the flow produced from the generator to control fuel oil pump speed, the deck pressure regulating valve, the supply air damper, and the supply air vent. These 4 things will maximize the efficiency of combustion taking place within the generator. On deck, there's the deck seal. This is a safety device that prevents the backflow of vapors into the engine room. So let's say there's hydrocarbon vapors on the distribution line and they start working their way back towards the engine room. It will reach the deck seal where it will put pressure on the deck seal water. The deck seal water will then work its way up the inert gas inlet, forming a water column of pressure that opposes the backflow pressure from the hydrocarbon vapors. Another safety device for the inert gas system are PV valves and PV breakers. PV breakers function similarly to deck seals on the principle that they operate on a water column. However, the PV breaker is pre-filled with a water glycol mixture instead of constantly being supplied with pressure. The PV valves, on the other hand, are mechanically operated, and and are used to protect the ship from over and under pressurization of the tanks at a much smaller scale. They are equipped with springs, lifting discs, and vacuum discs. The lifting discs will open at 2.5 psi, and the vacuum discs will open at a vacuum of 0.75 psi.
And the final system we have for you today is the fire suppression system. Now, the main goals of this system are to ensure the safety of crew, personnel, and the vessel in the event of a fire, as well as ensuring safety compliance and environmental regulations. Now, we know that this ship is going to be going from Honolulu, Hawaii, in between there and Long Beach, and we know that both of those areas are very heavily regulated. Now, the purpose of the system is to reduce dangers associated with MDO, LPG, and ammonia fires, and we're going to do that by providing multiple sources of fire extinguishing in a lot of high-risk areas in the ship, and this will all lead us to minimizing the potential dangers and damage that can happen to the vessel and the surrounding area. The fire suppression system types include a local area firefighting system, a fixed CO2 system, a dry powder system, and a fire main system. The local area firefighting system will be installed in the engine room and will utilize a cooling mist for water and oxygen displacement. It will be effective in combating MDO fires, as that will be used in the engine room for auxiliary machinery, and will focus on high-risk areas. The important specifications include a LAF pump that will have a 20-minute duration per 33 CFR 155 and a motorized actuated valve. Here's an overview of the system, and if we take a closer look, we can see the LAF pump has a 55.5 gallon per minute capacity, and each of the 8 high-risk areas will have a total of 2 nozzles each. The fixed CO2 system will be used also in the engine room, but for much larger scale fires, because it will scavenge the oxygen from the engine room space. Activation is manual or time delayed, and caution must be used with the system, as all crew must evacuate before the release of the system. When the system is released, all 159 CO2 bottles will be released from the CO2 room and will need to be fully recharged after the system finishes dumping. The enhanced pneumatic time delay will allow for 30 seconds for crew to evacuate per 46 CFR 7615. Again, here's an overview of the system, and if we take a closer look, we're going to go into the top right, and we're going to see valve number 1 and valve number 2. Valve number 1 is going to actuate and open the main CO2 valve, and valve number 2, which is also a pilot line, will actuate the CO2 cylinders from the CO2 room, releasing the CO2 into the engine room. The dry powder system was designed for cargo fires, particularly LPG and ammonia. We understand that the cargo is going to be held as a liquid, but upon a burst in the cargo tank, the atmospheric pressure will turn the liquid into a gas, and upon combustion, dry powder is the more suitable agent for this kind of fire. 2 fixed monitors will be placed port and starboard near the cargo manifolds, and 6 portable stations will be placed along deck. Here's an overview of the system, and we can take a closer look at the 2 larger components of the system, which are the nitrogen cylinders and the dry powder tank. The nitrogen cylinders will be used to pressurize the dry powder tank that will then allow the bicarbonate carate to exit out of the fixed monitors and portable stations. The fire main system is the final system that utilizes pressurized water hoses for a continuous water supply via self-priming pumps that serves as an added cooling mechanism to prevent structural overheating from the vessel. Important specifications include 2 general fire service pumps and 1 emergency fire pump that will be used in the case of unforeseen circumstances. Again, here's an overview of the system, and we can take a closer look at the pumps, understanding that the general fire service pump has an approximate 1,200 gallon per minute capacity, and the emergency fire pump has an approximate 300 gallon per minute capacity.
All right. The mission of this vessel is to make a trip from California to Hawaii every 2 weeks and discharge the cargo in a timely manner. The systems we design will allow the vessel to accomplish that mission and to accomplish it safely. Additionally, if properly maintained, these systems will be operable for the expected 15-year lifespan of the vessel. Thank you guys for being here today. You have any questions for us?
All right, it was 19 minutes and 59 seconds. Pretty good.